So today's notes are on solving trig equations, and if you remember last time we did not have a change in the argument, and this time we will have a change in the argument. So all that means is that when you have an equation, instead of just having sine of x equals a half, you're going to have something like sine of, 3x plus pi over 2 equals a half. So it's just going to change things a little bit, and I'm going to show you how that works out here in a second. All right, so 2 goals today. First, to solve a trig equation with a change in the argument for all real solutions. And second is same thing but on a given domain. So the only change is here it's on the given domain, and here it's just literally all real solutions. So we're going to walk through a couple examples. First example, cosecant of 2x equals 2. So the first thing I'm going to do is I'm going to say, okay, cosecant of 2x equals 2. And I'm going to change that to say this is the same as solving for where sine of 2x equals a half. Okay, so cosecant of 2x equals 2. I'm looking for sine of 2x equals a half. So I go to my unit circle and I say, okay, sine equals a half here and here. So that's pi over 6 and 5 pi over 6. So that means that my angle, or the value inside my argument, that quantity, has to equal 5 pi over 6 or pi over 6. So normally you just say, okay, I'm done. My answer is 5 pi over 6 or pi over 6. But now it's not that simple because we have an argument that's not just x. The argument is 2x. So this part that I highlighted here, that 2x, that has to equal 5 pi over 6, or that 2x has to equal pi over 6. Now we're solving for all real solutions. So remember we talked about where it could be pi over 6 plus 2 pi n. We could go around that unit circle an infinite amount of times. And same thing for the 5 pi over 6. So I have to add that 2 pi n in. So 2x can equal 5 pi over 6 plus 2 pi n, or 2x can equal pi over 6 plus 2 pi n. Now I need to isolate the x because the idea is that we're solving for x. So I'm going to go times 1/2, and that means this whole thing is times 1/2. So my left side becomes just x, my right side becomes 5 pi over 12, plus, and when I multiply in here, the 2's cancel, so it becomes plus pi n. I'm going to do the same thing here to get rid of that 2. And so this becomes x equals pi over 12 plus pi n. And then those equations represent every single possible solution to that cosecant of 2x equals 2. So let's look at another one here. All right, sine of 3x plus pi over 6 equals square root 3 over 2. So I'm going to look and I'm going to see, where does sine equal square root 3 over 2? So on my unit circle, that happens here and here. So that's pi over 3 and 2 pi over 3. So I know that my argument, that part that I highlighted in yellow, has to equal this angle or this angle. So I set them equal, and I say, okay, 3x plus pi over 6 equals 2 pi over 3. But again, remember that we can continue to add 2 pi to that solution to get more and more answers. And then I have my other half, which is going to be pi over 3. So 3x plus pi over 6 equals pi over 3 plus 2 pi n. Now I need to isolate that x. So what I'm going to do is I'm going to subtract pi over 6 from both sides. And if I get a common denominator, times 2, so 4 minus 1 is 3. So that gives me 3 pi over 6 plus 2 pi n. And now I still have to get rid of the 1/3, so I'm gonna, or the 3, sorry, so I'm gonna multiply by 1/3. And that gives me x equals, I'm gonna distribute into this first term, the 3's are gonna cancel, so I'm gonna have just pi over 6 plus 2 pi over 3n. And so that's my answer for the first part. I'm going to do the same thing with my second answer. So minus pi over 6 minus pi over 6. I'm going to get a common denominator. So that gives me 3x equals, and again, 2 minus 1 is 1. So pi over 6 is what I'm left with, plus 2 pi n. And I'm going to multiply by 1/3 to get rid of the 3 in front of the x. So now I have x equals pi over 18 plus 2 pi over 3n. And that's my other solution. So both of these together give me all real solutions for x for the second example. Okay, now let's look at what happens when we're solving on a given interval. So here's my first example. Cotangent of x plus pi over 3 times cosine of 2x plus 1 equals 0. So here's one of those problems where we have something times something equals 0. So I'm going to split it into two parts. And we've got cotan of x plus pi over 3 equals 0. And we've got cosine of 2x plus 1 equals 0. So my first part, cotangent of x plus pi over 3 equals 0. So I want to know, where does cotangent equal 0? So if I think about my unit circle, cotangent is x over y. So it happens here at pi over 2, and it happens here at 3 pi over 2. So I know my argument, the part inside the parentheses, which is my angle, has to equal pi over 2, or it has to equal 3 pi over 2. So I'm going to set them equal. I'm going to say x plus pi over 3 has to equal pi over 2. And then plus 2 pi n, right? Because I could go around the circle an infinite amount of times there. I can also say x plus pi over 3 equals 3 pi over 2 plus 2 pi n. I'm going to subtract pi over 3 to isolate my x. And I get, let me just scooch this down. And I get, let's see here, common denominator, so times 2 times 2 times 3 times 3, so 3 minus 2 is 1, so we get pi over 6 plus 2 pi n. And then over here, minus pi over 3 minus pi over 3, again, common denominator. So we get 9 minus 2, which is 7, so 7 pi over 6. Okay, so all of that went for this first part here. Okay, now I'm going to get to the part where the solution is between negative 2 pi and 2 pi in a second. But let's go ahead and solve this part here. So cosine of 2x plus 1 equals 0. So notice that the plus 1 is not inside the argument. It's outside the parentheses, so it's outside the trig function, outside the argument. So I'm going to subtract 1. Cosine of 2x equals negative 1. And now I want to know, where does cosine equal negative 1? And that happens here at pi. So I'm going to say, okay, that means my argument, this part inside the parentheses, has to equal pi. So 2x equals pi, and again I can add 2 pi into that. I can add 2 pi as many times as I want. And I'm going to get rid of this 2 out front, so I'm going to multiply by a half. So that's going to give me x equals pi over 2 plus pi n. Okay, and those are the solutions for the second part here. Now, the problem says it wants only the solutions from negative 2 pi to 2 pi. So what I'm going to do is I'm going to start adding and subtracting 2 pi from my solutions until I'm no longer on that interval. So let's start over here with x equals pi over 6 plus 2 pi n. If I add 2 pi to pi over 6, I know I'm already going to be outside of my domain. So I'm going to subtract pi over 6 minus 2 pi. And if I get a common denominator, times 6 times 6, it's going to give me a negative 11 pi over 6. And I know that if I subtract it again, I would be beyond negative 2 pi. So keeping in mind that we only want our solutions from negative 2 pi to 2 pi, this would be 1, and this would be another. Now I come over to the 7 pi over 6. And I know, again, if I add 2 pi to 7 pi over 6, I'm going to be beyond my domain. It's going to be bigger than 2 pi. So I'm going to subtract 7 pi over 6 minus 2 pi. Common denominator, so times 6 times 6. So that gives me negative 5 pi over 6. Yes. And that's where I'm going to stop because I know if I subtract 2 pi again, it's going to go outside of that domain. Now let's come over here. Here, keep in mind we're only adding pi because when we isolated the x, we had to multiply by a half. So if I add pi, I'm going to get a common denominator. That's going to give me 3 pi over 2. And I know if I add again, I'm going to be, let's see here, less pi times 2 times 2, so that gives me 5 pi over 2. And now I'm outside of my domain, so this is not a solution. So pi over 2 and 3 pi over 2 are my answers. Now I can also subtract, so pi over 2 minus pi, get a common denominator. 1 minus 2 is negative 1, so negative pi over 2. If I subtract again, minus pi, get a common denominator. So that'll give me negative 3 pi over 2. And that will be a solution also. And if I subtract again, it's going to be too far. So we've got this and this also. So those are all of my solutions. So it's a little bit tedious, but what you're doing is you're setting your argument equal to your angle, you're isolating your x, and then you're adding and subtracting until you're no longer within your range. We'll look at one more example together. So this one says cosecant of 5 theta times negative 3 equals 6. And we'll do this for, we'll do degrees this time. Theta between 0 degrees and 720 degrees. Okay, so I'm going to isolate my trig function first. So I'm going to go times negative 1 over 3 times negative 1 over 3. And I'll have cosecant of 5 theta equals negative 2. Now this is the same thing as cosecant of 5 theta equals negative 1/2, or sorry, sine of 5 theta equals negative 1/2. And I want to think about where sine equals negative 1/2. So that happens here and here. So this is 7 pi over 6 and 11 pi over 6. So I'm going to set my argument equal to those quantities. So we'll have 5 theta equals, oh sorry, we're doing degrees, my bad. So this would be 330 degrees, and this would be 210 degrees. So 5 theta equals 210 degrees plus 360n, and 5 theta equals 330 degrees plus 360n. So now I'm going to get rid of my 5, so times 1 over 5 times 1 over 5, and 210 divided by 5 is 42, and 360 divided by 5 is 72. And then over here, same thing. So 330 divided by 5 is 66, and then 360 divided by 5 is 72. So now I'm going to add 42 plus 72 is 114. If I add another 72, I get 186. Add another 72, I get 258. Add another 72, I get 330. And if I add another 72, I'm going to be outside of my domain. So these are all my solutions for that first part. And then I'm going to do the same thing with the 66. So I get 66 plus 72 is 138 plus 72 is 210 plus 72 is 282. And plus another 72, so will be the last one, is 354, and if I add again, I'm out of my domain. So these are my solutions. Okay, so all of those ones I boxed in blue are answers to that problem. And that's it.